Same as before. The only difference is, instead of creating a test statistic based upon a chi-squared, we're now basing it on an F value. We're going to use a slightly different chart, same concepts though, because as you see here, if sigma sub 1 is less, if the variance of 1 is less than the variance of 2, then you would accept the null hypothesis, and the opposite would be true. But here, our test statistic is going to be S sub 1, which is the variance for the sample divided by sample 1 divided by the variance for sample 2, and we're going to get a test value. Anytime now. So here's our rejection rule. All this should look very, very similar to what you've seen before. But instead of a chi-squared or a mu or an F value or T value, now you're going to get an F or T value or a Z value. Now you're going to get a variable F for your critical value. And here you're going to be more dependent upon the sample size once again, because you don't know the standard deviation of the populations per se. And so you're going to create a numerator, which is the number on the top, and then the number on the bottom, and you're going to create a p-value based upon the F distribution charts in the back of your book. That's a one-tail test. Two-tail test, same old, same old. The only difference here is you're going to have to, when you do a two-tail, you got to split those out, right? You got to split out. You got to split the error, the alpha, out to both sides of the distribution. You're still going to use this F value here. The sample size, or the standard deviation squared, otherwise known as the variance of 1 divided by the variance of 2. And here's your rejection rule. Note the F value at alpha over 2, because you're doing a two-tail analysis on this F distribution. Bless you. If you want to use the p-value approach, you'd get the p-value at F, and if that's less than the alpha, not the alpha over 2, but less than the alpha, then you would reject the null. Let's go through an example. Thermostats. We talked about thermostats before. And before, we knew what the standard deviation was for the population. But here, we're going to get two samples, and we're going to run two samples. We're going to compare the Thermo-Right thermostat against the Temp King's thermostat, and you're going to get sample statistics for each one, and you're going to run this test at alpha is equal to 0.1. So alpha 0.1, just like as before, when you get an alpha 0.1, what's the probability that you're right? What is it? Who's that over here? There's a female voice over here. Somebody, where was that? 90%. What's the probability that you're wrong? 10%, that's right. Just to anchor you to what you've known before. And so here are these 10 values, and these are samples, and you're going to create a sigma squared or an S squared for each one of these, and then divide the first one from the second one. Or the second one from the first one, actually. So here's your hypothesis. Same way as before, HO. Remember, and this was one of the things that everyone needs to remember in the quiz as well, is that for the null hypothesis, you always have to have some indication of equality. Here, it's very obvious, but in some situations, as you saw before, you get the less than or equal to sign. So the key is for this point forward is that you remember that the null hypothesis always includes some sort of equality. The alternate hypothesis is the opposite of what the null is. And you also make sure there's another, bless you, another key part of the exam is even if you come in and you say that your test statistic is greater than your critical value, you have to come back and formally reject or accept the null hypothesis. Okay, it's a key it's kind of an absolute, if you will. Now, if you don't come back and accept or reject the alternate hypothesis, okay, that's a little gray because everybody goes, well, you rejected the null, and so you would not obviously accept the alternate. But for sure, you have to declare I reject, or the research rejects the null hypothesis, or the research accepts the null hypothesis, or the research the findings were not able to allow us to conclude that we should reject HO. So here, you're going to get 3.18 as your test statistic, or your critical value. And the way you get that, and this back of your textbook, hopefully I've got that up here. Here we go. And this is why the distinction was made between the numerator and the denominator. If you'll go to the back of your textbook and look on your F distribution table, and it'll look like that if you don't have your book, but you go to your F distribution table, and it starts on page 981. Okay, 981. So here, what did you know? You knew that the numerator, oh yeah, a little bit, yeah. We'll just kind of share it, if that's okay. Yeah. You knew that the numerator degrees of freedom, they were both a sample size of 10, correct? So what's the degrees of freedom? N minus 1. So you have a 9, and then you had a 9. It just so happened that they both had a sample size of 10. And so you go, numerator was 9 degrees of freedom. The denominator degrees of freedom was 9. So you would say that this is the area in the upper tail is 2.44 at a 0.1. Because this is a one-tail analysis. See that? Go 9 and 9. Now, if for example, the second thermostat had a sample size of 8. Well, let's make it a little bit so you can use this chart here. But let's suppose this sample size over here was 9 instead of 10. Then all you would do is come up here until degrees of freedom 8. The numerator is still 9, and so you just run it across here at p.10. And there's a one-tail analysis. So your bogey is 2.56, or your critical value is 2.56. You calculate 2.53 they're using here. All right. This must be a two-tail. There's a two-tail, so we're going to use 3.18. Yeah, go back to that chart again. Sorry about that. Yeah, go back to that chart, and you're going to do a two-tail, so you divide it by half. So you're going to get an F statistic value of 3.18. See that? 9 and 9. Yeah, you got to divide that in half, so you get it 3.18. I thought it was a one-tail. So you're at a two-tail analysis. So your test statistic, or your critical value, is at p.05 instead of p.10, because you had to divide by 2. If it had been, if they said less than or equal to, what was the? I don't want to back up, but it was for sure. Back up just a little bit on this thing. Hopefully there was a two-tail. Yeah, it was a two-tail. it was an equal to, so that this infers a two-tail. It is a two-tail analysis. So you got to divide by 2, and that is your critical value, just like we did before. And so you calculate your test statistic by dividing S sub 1 over S sub 2. If you ran that sample and you did you calculated the variance, you would have S1 squared, or the sample standard deviation was 1.768. On the second thermostat, it was 0.7. Divided those two out, 2.53. 2.53 is less than F at a half of 0.10. And so what would you do? Let me draw this up. Oh, actually, it would look a little bit more like that. You can't have a negative value on F as well. 0.05, or 0.05, and your critical value was 3.18. Ran your test, brought your test statistic in. It was less than 3.18. So where are you? I'm using a marker this time on this chart. Do not reject. There's not sufficient evidence for you to reject the null. No difference. The only difference here is you're running a slightly different chart because you're working with the standard deviation for the samples. And here, if you went into the F value, degrees of freedom of 9 and 9, you would see that you actually didn't break the 0.10. So you would conclude the exact same, that it's not less than 0.10. So therefore, you would reject the null. There's nothing, or you would accept the null. There's nothing going on. Yeah, let's do this. Go to 1115, page 499. So that's all of you're doing an analysis of the variances. Right? And you're using sigma squared or S squared, depending upon whether you're working with a sample or you're working with a population. You run your 5-step analysis, as always. The only difference is you use a slightly different chart. And if you get a two-tail, don't forget to split those things in half. And how do you know if you have a two-tail or not? Let's get somebody else. Here, hold on. You do. Ashley, how do you know? How do you know it was a two-tail there? Hey, what?
There's no sense of direction.
That's right. Equality. Yes. So if you see greater than, less than, more than, enhanced, better than, worse than, you were obviously correct. Casey. See if everything's working still. Oh, yay, everything's working again. This is amazing. That's like 3 weeks in a row. So now, what we're going to do is we're going to switch this up on you. And we're going to start looking at proportions. And what is a proportion? If I've got 100 if I have 100 samples out there, or a population of 100, and 50 of them say, yes, we will, and 50 say, no, we won't, what's the proportion of those that say, yes, we will? 50%, 0.5. That's what I mean by proportion. If 75 of the 100 said yes, and 25 said no, and don't answer this, Casey, what proportion would be no's? 25%. That's what I mean by proportions. So you're not dealing with X bars, you're not dealing with standard deviations or variances per se, you're actually dealing with proportions. We've seen this before, but what happens when you get 3 or more proportions? You could keep running a population t-test, you could run 2, 3, but what happens when you get to 7 populations that you're trying to decide whether they're the same or different? I mean, you'd be sitting there all day, right, running t-tests. So for populations, all you're going to do is you're going to run a chi-squared, and this goes to your case study, by the way. I think we only have one chi-squared. So this is a chi-squared analysis, and and let's talk about that. We'll give you the simples. So here are the notations, and you have here's proportion for population 1, 2, and then if you're going to get, you may get 6, 7, 8 proportions that you're trying to analyze. So K represents any number of proportions that you're analyzing. And like I said, rather than going and saying, okay, I'm going to do a t-test on proportion for 1 to 2, 2 to 3, 3 to 4, 4 to 5, and then I'm going to come to 1 to 5, 1 to 4. I mean, you see how you'll be here all day running t-tests. Well, that's what this does for you, the chi-square analysis, much like an ANOVA, which is where you'll pick up the advanced course most likely. When you have different variances or different means, you'll start looking at the analysis of variance to decide whether you have a difference or not between 3 or more test statistics. Okay. So you might not. Some of the, I don't know what if they're on main campus. On the main campus, they might start here and go into chi-square and then ANOVA because it's a nice little lead-in. But I want to finish up here in chi-square because most of the other syllabi on the rest of the campuses don't really cover it, but I'm going to cover it real quickly as I can. And so your HO is, are those proportions equal or not? And or not is your alternate hypothesis. And if you cannot detect it, if you can't figure out if there's a difference based upon a chi-squared test, then you would not reject the null hypothesis. And then once you've determined that there is something going on inside that model, and we'll talk about this a little bit. Once you decide, and we're going to create a crosstab chart. Once you decide that model, there's something going on there, you can start working that model pretty freely. Because what you're trying to do is you're trying to understand, is there a difference between what was expected and what you actually came up with? Let's talk about that. Anybody, we've talked about this before. The Finger Lake homes, go back to our log cabins, A-frames, and colonials. Remember what we said about A-frames? They just look like an A-frame and they have a loft up top. Colonials, we call those, in the suburbs, they call them snout houses, or the urbanists call them snout houses because they're 2-story. And then a log cabin is a log cabin. And it could be, actually a log cabin could be a colonial, but let's not get into that. So these are actually independent as well. And the whole purpose of this analysis is to decide, is what you're observing different than what you expected? And that's what this calculations are going to be based upon. And here are your observed frequencies. Right? And so everything has to equal to one. You know, this would be actually have to equal 100% or 1.0 as normal. And as you come across here, 1.0. As you come down here, 1.0. And all these percentages have to add up to this percentage over here as a proportion. So if you had, well, let me just go to the next. So that's what you observed. Now your expected frequencies is, this is the formula, and divided by your total sample size. You take the I and the j intercept point and divide by the total sample size. Let me show you how that works. And here are the expected frequencies. This is what you would have expected to have occurred based upon the I and the j and the overall 360. So if you took, let me see, 135, and this all adds up to 135, and you would have expected that based upon the observed frequency, you would have to have about 75% would be colonial and 25% would be colonial. They would all be 135, so that'd be all the colonials, and then likely to repurchase would be about 75 versus 25%. That's what you would expect to see. And then we run an analysis of, here's what we observed, here's what we expected, and what is the difference between the expected and the observed, to find out if there's something going on in this model. Is there something to write home to Aunt Emma about, to Aunt Jane, or Aunt, I forget all the other aunts we had in here, okay? And so you come down here and you create this chi-squared value. And here's your rejection rule. Here's the critical approach. If your chi-squared is greater than the chi-squared of what you would, of the chi-squared at the test value that you're running, or the p-value that you're running the test against. For example, if you're running at p.05, this would be a chi-squared at p.05. And you're going to, and then you have some degrees of freedom that you have to take into account. So you go to the back of your text, and I'm not going to do this one because you can go to the back of your text as necessary. But what I'm going to show you here is that here is your value, your critical value of 5.991, and where you'd get that. Well, let's just go through it real quick. You'd go back to your chi-squared chart in the back, and then you would come up with this value of 5.991. And then you've got your test statistic. Here's the p-value approach. You determine that your test statistic is 5.067. It's less than 5.991. So therefore, what would you do? Do not reject. Cannot be rejected. And then it's going to actually, and then you can actually calculate the p.079. But what I want to show you here and that's what we concluded. So what I'm going to do is I'm going to take this and I'm going to put it into it's called Minitab, and this is what we'll be using, what you might be using in your advanced course, depending upon where you end up. If you go to Blue Ash, I think they're still doing it manually over there.